In this video, we are going to look at how to do hypothesis testing with two proportions. And then we're also going to look at how we can do this in StatCrunch. I will give you a heads up that you need to have an understanding of the basics of hypothesis testing, which if you haven't watched that video yet, I would watch that video before doing this video. All right, so if we want to compare two proportions to each other, we have three requirements that we need to meet. The first one is that the samples are from two simple random samples. The second one is that the samples are independent from each other, so we don't want the members from our samples to be related to each other in any way. And then the third one is that for each sample there are at least 5 successes and at least 5 failures. So we can check that one by taking our sample size, which is n, times our sample proportion, and then make sure that's greater than or equal to 5. And then we need to also take our sample size times the complement of our sample proportion, so that would be the failures, and make sure that when we multiply those together, it's greater than or equal to 5. And we need to do that for each sample. Now, once we get our requirements met, we want to go into our null hypothesis. Now, there's two common ways that you might see your null hypothesis. The first one is to write it as proportion 1 is equal to proportion 2. Now, another way that it might be written is that proportion 1 minus proportion 2 is equal to 0. Now, the reason that these two are equivalent is because if I have values that are equal over here, well, when I subtract them, I should get a difference of 0. For example, if I had 10 was equal to 10, well, when I subtract those, 10 minus 10, that gives me a 0. So either of these methods is an appropriate way to write our null hypothesis. Also keep in mind our null hypothesis is going to be the statement that contains the equality symbol. Okay, our alternative hypothesis, on the other hand, can take 3 different forms. The first one is just an indication that they're not equal, so we're not specifying which one might be larger or which one might be smaller. It would just indicate that our proportions are not equal to each other. So in that case, we would make sure that we have the not equal sign in each of our statements here. The next form that it could take is if we believe that proportion 1 is less than proportion 2, or we're trying to show that proportion 1 is less than proportion 2, our alternative hypothesis could have the less than symbol in it. If we are trying to show that proportion 1 is larger than proportion 2, our alternative hypothesis would have the greater than symbol in it. So our null hypothesis always has the equality sign, and then our alternative, it depends on what we're trying to show for our particular test. Now, once we have our requirements met and we have our null and our alternative hypothesis figured out, then we can go ahead and we can compute the test statistic. So when we are testing for two proportions, our test statistic is this formula right here. Okay, it is going to be a z-score, and it tells us that we take p hat 1 minus p hat 2. Now, p hat represents our sample proportion, and then the subscript of 1 is just how we keep track of the two different groups, group 1 and group 2. Over here, we have just a regular p sub 1 and a regular p sub 2. These represent our population proportion, but if we go back to our null hypothesis, we are making our null hypothesis is telling us that P1 is equal to P2, which we can also write as P1 minus P2 equals 0. So I can take this piece right here, which is this right here, and it's going to be equal to 0. So when I'm doing my test statistic, this P1 minus P2 is always going to be 0 when I'm testing two proportions. Then down here in the denominator, I have P bar and Q bar. Well, P bar is known as the pooled sample proportion. And to find that value, we have to do this side computation down here, where I take the number of successes from group 1, add it to the number of successes from group 2, and then take my sample size of group 1, add it to the sample size of group 2, and then I divide those values. So that's how we are going to calculate what we need right here for the p bar. And then q bar is the complement of p bar. So we're going to have to find a few values before we are able to actually use this particular equation. But this is going to produce our test statistic. So we're going to go ahead and look at a quick example here. So in a study of order accuracy for 2 fast food places in your local town, it was found that at Big Burgers, 287 orders were accurate and 26 orders were not accurate. From Jim's Drive-In, it was found that 153 orders out of 174 total orders were accurate. Use a 0.05 significance level to test the claim that both places have the same accuracy. Okay, so once we get a feel for what our problem's looking at, we're looking at order accuracy, and we want to test the claim that they have the same accuracy. We need to go ahead and check our requirements to make sure that it's appropriate to do this hypothesis test. So our first requirement indicated that we had to have simple random samples. We don't have a lot of information on how the information was gathered, so we're just going to have to assume that it was simple random. The next one is that the samples need to be independent from each other. Again, we don't really have a lot of information about how the data was collected. So we're going to have to assume that the orders that they gathered from Big Burgers was not related in any way to the orders that they gathered from Jim's Drive-In. Okay, our third requirement, we will have to check that one out. So I'm going to start by just making a list of some of the values that we're going to need, because we're going to end up needing them later when we do the test statistic anyhow. So in order to check our requirements, we need to know N1, P hat 1, and then we're going to need to know N2, P hat 2. We're also going to need to know Q hat 1 and Q hat 2, which are the complements of our P hats. So the N1 represents the sample size of our first group. Well, I'm going to let Big Burgers be group 1, and then I am going to let Jim's Drive-In be group 2. It's really not important which one you call group 1 and group 2 as long as you're consistent throughout your entire problem. So for group 1, for Big Burgers, they had 287 orders accurate and 26 that were not accurate. So to get my sample size, I have to combine those two values together. And when I add them together, I get 313. Now P hat 1, that's my proportion of successes that I need. And in this case, we're talking about order accuracy. So I would take my accurate orders, 287, divided by my total orders, and that's going to give me about 0.917 for P hat 1. Then Q hat 1 is the complement of P hat 1, so I would need to do 1 minus 0.917, and that's going to give me 0.083. So here's 3 of the values that I'm going to need in order to check the rest of my requirements. Now I'm going to do the same thing for my group 2. When I go and look at Jim's Drive-In, we found that 153 orders out of 174 total orders were accurate. So here I was given the total orders, so my N2 is 174. P hat 2 represents my sample proportion for successes. Well, again, we're talking about accurate orders, so I have 153 that were accurate out of my 174. And when I do that, I get approximately 0.879. And then Q hat 2 is the complement of P hat 2, so I need to do 1 minus 0.879. And when I do that, I get 0.121. So here are the 3 values, or 3 of the values from group 2 that I'm going to need. So now back to that third requirement. It says that when I do n times p hat for each group, it needs to be larger than 5. So I'm going to do group 1 first, and my n is 313. my p hat 1 is 0.917, and when I multiply those two together, I end up getting 287 with a decimal, which is definitely larger than 5. So we are good with that portion. Now still with group 1, I also have to check the q hat one. So I have to take 313 times my q hat over here, my 0.083. And when I check that one and multiply them together, I get almost 26, which is also larger than 5. So group 1 meets that third requirement. I need to check group 2 now. So now I'm going to take my sample size of 174 times my p hat, which is 0.879, multiply those together to see if it's larger than 5. And I get almost 153, so that one's okay. And then I need to check with q hat also. So I would take my 174 times my 0.121, and I just want to make sure that that's larger than 5. Turns out to be 21, so that's larger than 5. So now that we have verified all the requirements, we can go ahead and start on our actual hypothesis test. So the next thing I need to do now is I need to write out my null and my alternative hypothesis. So my null hypothesis, I can write it as proportion 1 is equal to proportion 2, or I could write it as proportion 1 minus proportion 2 is equal to 0. Either one of those would be fine. Now my alternative hypothesis, I need to go back and read to see if there's any indication that we're trying to find that one of them is higher or lower than the other. And as I read through this last sentence here, it just says test the claim that both places have the same accuracy. So there's no indication as to one being greater than the other. So we're going to go ahead and just go with the not equal symbol. So I could write that as P1 is not equal to P2, or I could write it as P1 minus P2 is not equal to 0. Either one of those would be appropriate.